Hi, Juan Paul. Yeah, okay, so I think we can start right now. All right, let's open something that I will be able to see the chat also. Okay, I can minimize. All right. So today we are continuing the credibility theory, the topic that we were talking about for the previous week, and also there might be some trespassing to the previous week. So if you see something familiar, that's okay. And we are going to, let's say, going through the spiral to introduce uh, to introduce a new material with the basis on the previous one. So today we are dealing with credibility theory, and credibility theory in general insurance is essentially a form of experience rating that attempts to use the data in hand, as well as the experience of others in determining rates and premiums. So this is actually something which I have. This is actually something that we are going to set the premium for ourselves. Let's say that we are an employer, we have several workers, and we want to find out what premium to set for our particular workers. And we are going to do that on the basis of other employers which might be the same kind, and basis on that experience, we're dealing with the several years of, let's say, claims that happening in that insurer, get this information and derive the premium for ourselves. So, and actually, an interesting and early historical example of the use of credibility theory deals with the setting of premium rates for employers to cover for workers' compensation. And it happened in the early 20th century. So the challenge to an actuary, so we are acting like an actuary, the guys who set the premiums, who analyze the background of the insurance, the economical situation, everything, and find out the risks actually. So the challenge to casualty actuary was often to balance the claims experience of a particular employer with that of all employers having similar working practices and conditions in determining premiums for insurance coverage. Okay, Danielle. Okay. So today we address the challenge of trying to estimate expected future claims. Okay. We estimate the future claims and maybe aggregate claims for a portfolio of policies on the basis of limited sample of current information X, and where other collateral information is also at hand. So basically that what we are dealing with. So let us assume that there is a crucial parameter of interest denoted by theta, which, for example, may be the annual claim rate for a related expected aggregate claims total. Often there is other collateral or prior information from business or portfolios of a somewhat similar nature, and this might be useful to estimate this parameter theta. Okay, let us denote the theta s, this thing, an estimate of theta based on the sample information X, and this theta C. Actually, this theta S and theta C, they need to be with the hat, okay, because this is the estimate. So theta C is an estimate theta based on the available collateral information. Okay, so in this situation where theta is mean, then theta S might be the sample mean X, and theta C some prior estimate of this mean. Okay, let's consider a credibility estimate of theta as a linear combination of the sample estimator and the collateral estimate theta c of the particular form. So what does it mean, linear combination? We have something times something plus something times something, okay? And the first thing is actually the theta s, and the last thing is theta c. So we have to multiply it on the something which in total is 1. So if we consider the parameter, let's say the parameter z, our theta s and theta c will complement with the linear combination, and this thing will be called the credibility premium formula. This is the general expression. And traditionally, there has been an emphasis on only using estimates theta s of the form of these linear combinations in the credibility premium formulas. So let's start with the first example. So far that might be overwhelming, but actually what we were talking about, we describe the credibility premium formula. So this is the single piece of information you have to keep in mind, and z theta s plus 1 minus z theta c, this is the thing which we need to know so far. Okay, so let me open RStudio. We have annual claims to 4 rural churches over the past 3 years, averaged at 24,000, and we are asked to quote a pure premium theta to insure them next year. Also available is very extensive data on claims data from churches in the capital city of the country, where the recent average annual amount of claims per church was 8,000. So this is the same situation as for workers' compensation. We are trying to understand the premium which we are going to set based on the other information. Okay, so now we are dealing with this kind of exercise. Okay, so relying exclusively on the directly relevant and limited information from the rural churches, we could estimate, so our, let's say that will be, okay, so here is example 1. And, the information theta is actually 24,000. This is the given thing. And we are going to be using the collateral information from the extensive city, and this collateral will be 4 times 8,000. This will be 32. And a credibility approach would use both sources of information and estimate data by this linear combination. So the actual formula will be z times these 24,000 plus 1 minus z 32,000. Okay, so this is the information which we are able to obtain, and we actually shall investigate several approaches to this credibility problem. So in the classical approach to the credibility theory, concern centers on establishing when there is enough data to use z equals 1, that is, give full credibility to the data. So this actually z equals 1, that means we are sticking with 24,000. And if this is not the case, how does we determine the reasonable value of z? This is basically a frequentist approach to credibility, and is often called either limited fluctuation or American approach to credibility theory. So actually, let me open. Are there any questions so far? Okay, I guess okay, good. So there might be suggestions to the credibility factor, and this credibility factor might be set as okay, so where I should let me change chunk output to console. So there might be suggestions of using Z such that there might be P over P plus K, and let me explain what that means. So P represents the earned premiums. P is earned premiums. And K is determined by judgment. Okay, so let me also set something in the global options a little bit larger, maybe 25. Okay. So this is the classical approach, right? The American approach to credibility theory, where we stick with obtaining Z as P over P plus K. And in the Bayesian approach, there is the different approach. Let me check if we have it. Yeah, this is the classical approach. In the Bayesian approach for credibility, the credibility estimate is based on posterior distribution of theta. And the credibility factor is Z is the weight of Z and 1 minus Z, okay? And there is a next approach, the Bullman approach, which we haven't been, the Bullman, actually, this is the German word, and there should be double dot on the U. This is umlaut, the special character for German. So sometimes there will be the appropriate naming of Bullman, but I'm just saying that B, U is double dot should be here. So he popularized this kind of Z equals N or N plus K. And what the credibility factor of Bullman, K is the ratio of the mean. Okay, so this K should be in Bullman. In Bullman, K should be the mean of the process variance to the variance of hypothetical mean. Okay. So this thing actually is the basic model Bullman, and on top of this Bullman model, there is also the Bullman and Straub model, which generalizes to the situation where the exposure units, for example, number of policyholders, may vary with time. Okay, so we consider Bullman. This is the new point of information here. Well, in the last lecture, we haven't considered it, and now we will do that, and we will do that in like step-by-step manner. So we start again with the classical credibility theory from full to partial credibility, and then we will come to the Bullman credibility. Okay, so let me show. So if we are talking about classical credibility theory, what can we say about full credibility? If you're ready, we can deal with this example. If you have any questions, please let me know. Something strange happening with my mouse. Oh, you don't see the screen. Okay, sorry for that. Hold on. But share screen is on. Share. Do you see it? Okay, so this is what we have been talking about, we set the, for example, we set the theta is 24,000, and actually this is the thing, the z is the credibility factor, z is 24,000, and 1 minus z times 32,000. This is the information we can get in the form of the average, of the weighted average. Okay, so z actually might be the p over p plus k. Okay, and this is the American approach to credibility theory. And in Bullman, this is the new point of information. So k is mean, and in Bullman we are talking about z equals to n over n plus k. Okay, so here k is the mean of the process variance to the variance of hypothetical mean. Okay. So far everything should be clear. Okay, so first we are dealing again with the classical credibility theory, the American credibility theory, and this is the task we have to stick to. So aggregate annual claims. We have controls. Okay, aggregate annual claims modeled by a compound Poisson distribution with Poisson lambda and typical claim size X. Okay, what do we need to find? Claims collected for given approximately. So this is the task without numbers, but we are able to determine those numbers by ourselves actually, but we need to derive the formulas here. So actually P, so we have to set the formula for our lambda. Let me check, do we have these formulas set? Yeah, okay. So we have set the formulas over here. The variance of this parameter lambda ex squared, we know that, and we can derive the formula for p. P will be larger than 1 minus alpha. This is like a long derivation for this kind of formulas, but still the value of make it smaller a little bit. So the value P of S minus theta, this actually will be larger than equal to 1 minus alpha. And after we have set this kind of S minus theta here, okay. And after we have set this kind of thing, this is less than or equal to K theta, we can find out that our lambda is actually this value. So we will place the how to say, we will place the numbers inside those kind of formulas in order for you to get the idea of what is happening here. So CV squared is the coefficient of variation. So last lecture we also used coefficient of variation, but still to remind you, the CV is the square root of variance over the squared mean of X. So this will be actually standard deviation divided by mean. And this is the coefficient of variation of the random x. X is the claim size. Okay. And 1 minus alpha over 2, this will be used as the quantile of normal distribution. This is like the standard thing when you encounter z squared to the power of 1 minus alpha over 2. This this thing is okay. We are recording. Everything is okay. This thing will be determined with the normal distribution, the quantile of normal distribution, and that's why we're using actually R, because it is relatively easy to find out all this kind of information. So in order for us to approximate S with normal, we will use R lambda, which is this thing. CV is given, Z is just the quantile, and K squared is the only thing of the only parameter that we have to set inside. So let's say that we place some numbers. Example 02. Let's place some numbers. Let's say that we are dealing with parameters K alpha, and they are given like 0.1, let's say, and 0.05. So we have this kind of parameters. Suppose that claims are exponential. We might choose different distributions, but for easiness, we said that the claims are exponential distribution of claims. Okay, and if we are dealing with the exponential distribution of claims, then we know that from the distribution EX squared will be 2E squared X. So this is by definition. And for full credibility, 0.1 and 0.05, one should have at least that value of R lambda claims. So let's calculate. Actually, we need to find out the Q norm of 0.975. So how much it will be? It will be 1.96. So we will place this quantile. Why 0.975? This is 1 minus 0.05 over 2. Okay, so we are placing actually this number inside there. So Q norm of this value, and it gives us 1.996. This 1.96 we divide over 0.1, the K value. So let's say K equals to 0.1, alpha equals to 0.05. Then we replace here with alpha. Then we replace here with K, and make the whole calculation squared, and times okay, so sigma x is actually sigma over 2e squared over e squared. So the variance is lambda ex squared. This is the variance, and we are dealing with only lambda, so here will be only two, these two from here. So K alpha and Q norm. So we will have this number 768, and this actually we make it we make it seal of this number, and seal of this number is 769. So we need 769 claims, okay, to make to make the full to ensure the full credibility, or to put the full credibility on S, on this parameter S. Okay, let me check any. Where's the meeting? Sharing the screen, and I don't see any. I don't see actually any chat. Where's the chat? Okay, that's strange. I don't see any chats so far. Okay, guys, do you hear me or see me? I see participants.
Yes, hear you, but didn't see you.
You don't see me.
Yes. Yes, now it's okay.
Okay. Because everything is really awkward here. Okay. So chat, yeah, now chat is available also here. Read controls. All right. So we have just proved that we need 769 claims in order to make sure that we put the full credibility on the value of S, on this kind of value of S. Okay. So next, in particular, if the annual rate of claims was of the order of lambda, which is 160, then we would have full credibility, 0.1 and 0.05. In how many years, actually? So if our lambda is 160, how many years do we need to ensure the full credibility? So this is a question for all of you. So we have 769 claims. This is the requirement to ensure the full credibility of our S. And if we have only lambda is the number of claims, right? So if lambda is 160, and we need to collect up to 769. In 1 year, we'll have 160. In 2 years, we will have 160 plus 160. So how many? So this is the calculation. We have 160 times 5, and this will be 800 claims, which is larger than what we need, and this is okay. And we can say that in theory, the estimator S, the sum of this S1 plus S2 plus and so on, over 5 differs from that theta by the most 0.1 ES. Okay, let me check again. So the estimator S, which is the sum of SI, and here we have over 5, differs from ES by most 0.1 times ES with the probability of, what is the probability? 0.1 is this thing, and the probability is another number. So 0.005 is, this is the like the complement to 1, and the probability is actually 0.95. So the probability of at least 95. Now suppose that instead that the parameter of interest is the annual claims rate lambda as opposed to the pure premium ES equals to lambda EX. And if we want to use the observed average annual rate to estimate lambda with full credibility, we will need to use that R lambda, which is the form of that. So let me make it here. So this is the this is the value of R lambda, which is needed for us to estimate lambda with full credibility, K alpha. And unless X is constant, we have this value, EX squared over E squared X, which is larger than 1. And it follows that we always need more claims experience to estimate pure premium than a claim rate. Okay. This is not surprising, since for pure premium we allow for variability in severity. What does it mean, severity? This is the claim size. So we have frequency and we have severity. Frequency is how frequent the events happening, and severity is how tough these events are. So if there is a car accident, there might be a small amount of dollars involved, and there might be the total crash, which have the huge amount of dollars involved. So the severity is how hard the event happened. And the variability in frequency, the claim rate, okay? For an exponentially distributed claim, the ratio of EX squared over E squared X is 2. EX squared over E squared X is 2. And for log normal distribution with the parameters, it will be exponent to the power of sigma squared. And actually, these values are estimated for many types of insurance claims, and they generally are between the values from 2 to 5. Okay, so these EX squared over E squared X might be from 2 to 5. All right, then we are ready actually to derive the formula for MQ. And before that, do you have any questions? So, all right. We consider the situation where annual aggregate claims, let me check, where annual aggregate claims S are modeled by a compound distribution, but where N is not necessarily Poisson. And using, again, we always use the normal approximation for these distributions, as we have been talking about lecture 10. Also, using this normal approximation for S and arguing as above, when R equals to 1, it is clear that we can achieve full credibility. We can achieve full credibility, K alpha, by using S to estimate theta. So we are going to use the same parameters Z over K. And if we are talking about compound binomial, where the number of claims is like that, then the full credibility is achieved with these parameters. So let's say that total claims S for a year result from an exposure of M units with claim frequency rate Q equals to 0.002. So Q equals to 0.002 per exposure. And typical claim is exponential. Okay, typical claim is exponential. Then S is fully credible if, so we in place this Q parameter 0.002 in this equation, and this thing, do you remember what this thing is if we are talking about exponential? This thing when we are talking about exponential. Okay, so please write in chat. What is the value of EX squared or E squared X given exponential distribution? This thing. Anyone? Just write this simple number. This value is actually 2. It should be 2. This thing for an exponential distributed claim ratio is given EX squared over E squared X is 2. Okay. And using this thing, so this thing is 2, then minus Q is minus 0.02. And we have the whole thing is how much? Anyone? Please write in chat. So EX is the mean of the distribution, and the variance is the variance of the distribution. This is the where, so EX squared or E squared X, so this is the sigma over mu. This is the same thing as we were talking, let me say, this is the same thing over here, actually. So EX squared or E squared X, then we will be dealing with that. And this parameter is given. So I was asking, what is the value of this parameter? Okay, this value of the parameter is 2. Then you are having Q, and we are assuming that Q is given as 0.02. Okay, so the whole thing is how much? Two minus 0.02. Okay, and this thing is actually 1.98. Okay, 2 minus 0.02. This is 198. So this thing is I'm sorry. This thing is 1.98, and we multiply MQ more or equal to Z over K times 1.98. On the other hand, if the interest is only on the parameter En, then En equals to MQ, and the expected number we will make it as 0.98. So EX is 1, and this thing will be z squared over k squared times 0.98. Okay, so next we have to talk about the partial credibility, and actually there might be this thing. We often we don't have enough data to justify using full credibility to estimate a parameter, and the question therefore arises as to how much credibility or weight z to put on the sample information. And the most commonly used method for assigning partial credibility is the square root rule. Okay, square root rule, whereby the credibility factor z is given by square root of n over nfk alpha. This nfk alpha. So the justification of this formula is that with this value of z, one limits the fluctuation of variance of z times x bar around z theta that would be obtained if the data were fully credible for theta. Okay, suppose we want to estimate the value of theta equals to ES. Okay, let's suppose partial credibility. So if we want to estimate the value of theta equals ES equals lambda times EX. Okay, so let's place this things. So if we want to estimate these four compound Poisson distribution, and we have our years of aggregate claim data S1, S2, S3, and so on SR, we know from the equation that for full credibility K alpha, we will need this value or this value for the full credibility. And if we do not have this amount of data, then we will use ZS plus 1 minus Z mu 0 to estimate this theta value, where Z is from 0 to 1, and mu 0, this thing is collateral estimate. 0 equals to collateral estimate. We are going to estimate this value of theta with this collateral estimate and z value from 0 to 1. Okay, suppose we decide to use a value of z so that zs, this value, zs, as an estimator of our z theta. And we place some credibility K alpha on this value. So what will be the equation? The equation is given here. Our lambda will be that thing, and the credibility factor will be determined with this square root. Okay, let's see. S actually, this depends on the problem statement. So generally, S is the number of claims collected over the years. Okay, so let me place S, number of claims. And there might be different values for S, and actually we are aggregate annual claims data. So S, this is the number of claims per year, S1, S2, and SR. And we are collecting these claims for several years in order for us to make sure that we are credible for our estimator of how many claims will be. How many claims there will be, that means that ES, expected value of claims. Okay. So that was a really good question. Thanks. Okay, so we are ending up with this kind of formula, and I think that it's enough for now. We will have to make the stop and break for 10 minutes. If you have any questions, please write in chat. Thank you. I'll share.